This is lecture 19, the last lecture in this lecture set, this course, called the first isomorphism theorem. It's part of a pure mathematics course at junior and senior level on the topic of finite group theory. The first author of the textbook that I use is Barnard. Here's the text. It's in the Teach Yourself series called Mathematical Groups. Now, this lecture, it's been a week since I've last camcorded. The reason for the week's delay is essentially due to YouTube, the very slow uploading times. It takes me about 4 or 5 hours to upload, say, 12 minutes of filming. I had such a backlog that I just waited. Now, this too is an experiment. As you probably know if you've been following these series closely, I am a night person, and it is now 8 a.m. Now, that doesn't mean I've got up early. It means that I haven't gone to sleep yet. And this is an experiment in the sense there is quite strong sunlight streaming in through the window, even with curtains drawn, into this bedroom where I'm recording. So I'm not quite sure, again an experiment, whether you may be seeing a reflection from the window just behind the camera that's disturbing your view of the board. I don't know. I've not. I can only know by looking at the result. So if it's fine, fine. If it's not, well, I've learned something. Okay. All right. This lecture will be pulling various strands of theory together, and then actually applying them. So I have enough whiteboard. I'll give 2 examples of 3 of pulling together one of the examples that we did in the previous lecture and theorems 62 and 63. So think of this lecture and this session, this board, if you like, as a kind of consolidation, okay, where we're bringing various strands of theory together. So I'll start with a bit of revision, because you need to know which strands are being pulled together. So I guess the essence of this session is down here. I'm jumping ahead a little bit, but just remember that. Okay. So some revision. So you have a normal, usually N for normal, a normal subgroup of your group G. So you're creating, so if N is a normal subgroup, you know that you can create a quotient group or factor group of this form, right? Using your normal subgroup as in a manner of speaking, the divisor, if you like. Remember, this is just a label in a sense. This is shorthand for a set of cosets that you form from your normal subgroup, and using what I called subset multiplication to multiply 2 cosets together to get another coset which is a member of your set of cosets, this quotient group. Okay. Now, in the particular case where this mapping F is of this form, so if you're mapping it up, so this is mapping a group to a group, and this is mapping an element to an element. Now, in the case of a quotient group, your elements are sets. So quotient group is a set of sets. Okay? So you're mapping an element of G, X is just a member of G, and you're mapping that to a coset, right? X of N. And N is your normal subgroup that you form the quotient group with. Okay? Yeah, Xn. And previous lecture, lecture 18, we showed that this mapping, this f, this function, is homomorphic, which I've just shortened to homom. Alright, so we've done that. So, yeah, this is all revision. Okay? Now, with a quotient group, it's a group, therefore it must have a unit, right? A unit element, which in this context is what? Well, the unit coset is En, right? When x is E, and you can show that pretty easily. Okay? So, but En is just N, right? So your unit coset for this function is just N. It's your normal subgroup. That's your unit coset. Okay. All right. So which elements belonging to G map into this unit coset? Which if you think of this as H, so the general mapping between two groups, mapping G into H. So think of this as H. So this unit here, which is just N, is your unit of H. Okay. So in asking this question, which elements belonging to G map into your unit element? That ring a bell? So you're asking in effect, what is the kernel? From last lecture. Remember, the kernel is always elements in the kernel's a subset, all of whose elements map to the unit of H, the unit of your group that you map to, the target group, if you like. All right. So this question here is, what are your members X that map to the unit of this? And then we know the unit of this is just N itself. Right? We proved that last lecture. Okay. If you're not following this, or you're a bit rusty, really go back and study chapter 18 thoroughly, because it's critical for understanding this one. Okay. All right. Yeah, so just saying here. So last lecture we showed the set of these x's that map to N is itself N. Right? So that's a critical result. And last lecture we also showed, again, a bit more revision. In fact, right down at the bottom here is revision, effectively. But need to put it all together. If two elements from your G, X and Y, if they both map to the same element, right? So if f of X equals f of Y, that's true if and only if these two elements from G in the same coset of your kernel. Okay. All right. Now let's start pulling things together a bit. Now the kernel, it's where we proved last time that it's a subgroup. It's a normal subgroup. Okay. So this N here is like a general case of a normal subgroup, and here's more a specific case. So we can put in this, we can use this K as the kernel as an example, so like a more concrete case of N, right? So I mean, this N here is general, but we could substitute for this N here. We could put K here, right? Because N is just a normal subgroup, but K is a normal subgroup, so we could put this K here. All right. So if we ask then what elements of G, X here, map to this normal subgroup, K. So this here is just the same as here. Now that's important, what I just said. Okay. Now K is just a particular example of a normal subgroup. This is true for normal subgroups, provided that, given this mapping, of course, specific to this. All right. So we're now asking the question: what are your solutions, in a sense? What are your x's such that they map into the kernel? Is that right? Hold on. No, they. Well, take that back. Such that f of x equals the kernel, right? So, so that these x's map to the unit of h. In this case, it'd be g/k, right? Now, in general, if you map any little g, which is just a member of big G, and you get a, some element a. Now a is just some solution, some element belonging to h. Now a will belong to the coset a k, right? That was one of our theorems. An element a belongs to well, AK, the kernel, and the kernel's a subgroup. Therefore, it's a group. Therefore, it has a unit E, right? And A times E is just A. So this A here is a member of this coset AK, right? Which before we've written just as A bar, right? And for different values here, like if you have like G1 and G2, little G1, little G2, and they both map to the same value, like A here, then those little G1, G2, they will belong to the same coset of K, which is of the kernel. Right? That's theorem 63, right? So so if you have little G1, little G2 having a different value, then they may belong to different cosets. And remember, a group is the union of disjoint cosets. Remember that? So we now have a way to find solutions to this problem. What elements of G map to a particular value? That's what I'm calling the problem. All right. So if you were asked to solve something, and still talking in the abstract, and from here onwards, we'll give, well, on this board, two concrete cases, two examples of using, trying to find solutions to this kind of problem. The problem being, what are the values of x, or little g if you like, same thing. So this x here is a member of your group big G. Okay, so if you're asked to find this solutions, x, little x, to this problem, what set of elements x map to A, to the solution A, to this element A, and A will be a member of your H